Recall that in the last video, we set up a system of linear equations. So we had this. We had dx by dt, which remember we can just notify by dot. We could just see, for convenience, we can use dot notation here. So we had dx by dt is given by this linear combination of x and y. So we have ax plus by plus k1. And then dy by dt is this linear combination, which is cx plus dy plus k2. So this is just a linear combination. Well, we can take these two equations and we combine it as one, using vectors and using matrices. So we can write these two equations, combine it into this. Dx by dt, where x is a vector now, is equal to ax plus k. Notice that we're using vectors here because x, of course, is just xy. Okay, and a is our coefficient. Okay, so this x basically is not the same as this x in here. Right? This is a vector. Okay, and then we can look at that. And then we can make a transformation. So we can, when we set this equal to 0, we'll come up with an equilibrium point, which of course is the max, corresponds to the maximum or minimum value, which is kind of what we're after. But that equilibrium point won't necessarily be at 0. So because this is a linear system, we can make a really nice transformation, which is this. This is x tilde. And we're basically just shifting it to the left by y and down by x. Okay, and we're moving this equilibrium point, which comes out here, to 0, 0. Okay, so that makes it much easier. And we can do that because it's a linear system. For the non-linear case, we can't do that, and we have to be a bit more clever. Okay, but now if we differentiate this, we end up with that. So basically, we're now dropping the k, and that's nice. So this is where we end up. Okay, so we've got dx tilde by dt equals ax tilde. Now, for convenience, I'm actually just going to drop the tilde. So I'm going to end up with dxt plus ax, and also going to drop the, equals ax. And I'm actually just going to drop the vector notation as well. But yeah, this is what I mean. So for convenience, I'm just dropping the tilde in the x vector. But when I write this, this is actually what I mean now. So just making that point now. So it avoids confusion. And we assume, of course, that we're at 0, 0 because we've made this transformation. Okay, to make it 0, 0, x tilde. Okay, and we want to look for a solution of this form. So x, and that will be of a function of t, all right, because it's differentiated with respect to t. So we're looking for a solution of this form. So we're going to have e to the lambda t times u. Now what's going on here? I'm actually going to drop the u notation, but that is actually a vector. Okay, what's going on here? Well, basically this is eigenvectors. Eigenvectors and eigenvalues. This lambda here is our eigenvalue, which comes from a. Okay, and this is our eigenvector, which we can get from lambda. Okay, and if you're not sure what eigenvectors and eigenvalues sort of mean, it will become clearer later on, but I recommend going away and just doing a quick revision on that. All right, so if we now differentiate this, so I'm going to now drop the x of t, I'm going to drop the function of t, okay, for convenience again. So I've got dx by dt. Okay, if I differentiate this with respect to t, what am I going to end up with? I'm going to end up with lambda e to the lambda t times u, okay, where u is just our eigenvector. All right, and so now if I do a bit of rearranging, okay, so if I take this and if I multiply both sides by a, our coefficient matrix, ax, so I've got ax equals, what do I get? I get, this is just a constant, e to the lambda t is just a constant, and then I've got a times my vector, u. All right, and so why did I do that? Well, this here is equal to the right-hand side of our equation, and this here is equal to the left-hand side of our equation. So I can now say that lambda e to the lambda t, u, is equal to this, e to the lambda t, a, u. All right. And notice that if I just take off my constants, this is a constant, this is a constant, then I get lambda u equals au, all right? And then if I take out, if I move this left-hand side over to the right-hand side, so I get au minus lambda u, that's going to be equal to 0. Take out a u, I get a minus lambda I, or a minus lambda, it doesn't matter, because u is a vector, equals 0. And you should recognize this from eigenvectors and eigenvalues, all right? Hopefully you should. remember that this should be an I here, I think. Yeah, because I want to multiply this by u, so it doesn't matter. But I'm going to put an I in there just for convenience anyway. Yeah, you should recognise this from eigenvectors and eigenvalues. If you have the matrix, our coefficient matrix, which we want to find, A, B, C, D. Okay, this is our coefficient matrix. And then if I do A minus lambda I of this, so I get A, B, C, D, remember, multiplied by 1, 0, 0, 1, I will get and that is times by lambda as well. Okay, so this is times by lambda, so therefore I can just change this to lambda here and here. I get A minus lambda. Sorry, that's not right. That should be a minus in there. Okay, so I'm going A minus, this is lambda I, this is A. All right, so A minus lambda plus B times 0, that's fine. And then I've got, what have I got? So this is 0. This is C times 0. C minus 0. Which is C. Sorry, I'm making a right mess of this. Let me start again because this is making a right mess of this. Hopefully you're sort of with me. This is A. This is A, B, C, and D, right? And then I want to take away lambda I. Well, lambda I is just leading diagonal lambdas. All the other elements are 0, 0. All right, so I get A minus lambda. I'm trying to multiply instead of subtract, I think, before. So A minus lambda, B minus 0. C minus 0. D minus lambda. Yeah, that makes a lot more sense. All right. And then if I take the determinant of this, okay, so if I take the determinant of A minus lambda I, all right, and set it equal to 0, so I'm taking the determinant of this, I get A minus lambda times D minus lambda, and then I take away B times C, and I set that equal to 0. All right. And then I expand this thing out, so I get AD. What do I end up with then? I end up with minus A lambda minus D lambda. All right, I'm going to rewrite this as minus A plus D lots of lambda. Okay, hopefully you can follow what I've done there. And then I just add lambda squared, and then I've got a minus BC here, and that's equal to 0. So if I just write this out in conventional quadratic form, I've got lambda squared here, minus A plus D, lots of lambda, all right, this is a D, lots of lambda, and then I've got plus AD minus BC is like your constant term on the end, that's equal to 0, okay? So convenience, I'm going to write this as lambda squared minus, I'm going to do minus, yeah, I'm going to write this as minus P lambda plus Q equals 0. Okay, where P is something called the trace of the matrix A. Okay, so P is the trace of A, and that's just the leading diagonal. So A and D just added together. All right, so that's equal to A plus D. Okay, and Q is just going to be equal to the determinant of A. Okay, so that's determinant of A, and that's clearly just going to be equal to AD minus BC. So again, just a reminder of linear algebra there. If you're unsure on anything which I've done there, just go back and have a look. So let me just try and make this a little bit smaller and put it into one neat little form. Okay. So we've got that. Cool. Okay. So what are we going to do now with that? Well, now we can solve this. Okay, so we've got lambda squared minus P lambda plus Q equals 0. We can solve this, and we can solve it using the quadratic formula. And because it's a quadratic, we know we're going to have two roots. Let's call it lambda 1 and lambda 2. Okay, so let's solve it. So we've got minus P. Well, this is going to become P, isn't it? Plus or minus the square root of P squared minus 4AC, so minus 4 times 1 times Q, so minus 4Q, and that's all going to be over 2 times A, so 2. Alright, and that's how we get now our eigenvalues. This is all I'm doing, I'm just finding my eigenvalues of my matrix A. Alright, and if I do that, okay, so let's say that lambda 1 is not equal to lambda 2, alright, then are you happy that the corresponding eigenvectors, we're going to get u1 and u2, all right, are going to be linear independent. So in other words, they're not going to be the same. All right, we call that linear independency. And so therefore we can write it as a linear combination. So we've got x of t is equal to c1 e to the lambda 1t times u1, okay, plus c2, so there's just c1 and c2 are just some constants, they're just some number, it doesn't really matter to the overall thing what's going on, lambda 2t, and this is going to be u2. Okay, so basically all I've done is I know that my solution, where are we? I know that my solution of, further up than this, no? Yeah, I know that my solution of this thing here, is going to look something like this. All right, something like this thing in here. Okay, and I've just shown that just by doing linear algebra, linear maths, that I can basically rewrite my solution. So where are we? This thing here, sorry, I'm reading the wrong thing off. This thing, I know my solution is going to look like that. So basically, just by doing linear maths, I've shown that if the eigenvalues are not equal to each other, then the eigenvectors are not equal to each other. So then I can write it as a linear combination like this. Okay, it's again just another proof in this video. All right, and note as well that the eigenvalues, these things here, are going to be what drives the solutions. Okay, so what we're going to do now is we're going to consider different cases of these eigenvalues. Okay, so what happens with differing values of lambda 1 and lambda 2, and see what all the different options, the different outcomes are going to be. And that's going to be in the next video.